My name is Tore. I come from Zama, and I'll be talking now about the Zama threshold key management system, the TKMS, threshold key management, or threshold key generation and decryption for EVM chains. So for the talk today, I will start with a bit of a motivation of why do we care about key management and which setting I'm actually considering, and just a brief outline of what we're actually achieving with this. Then afterwards, I'll start to dive in a bit more into the details and how we ended up in this situation and why something that seems so easy is actually not that trivial. Okay. So we've been hard at work at Zama on adding fully homomorphic encryption to EVM blockchains, right? So on a normal EVM blockchain like Ethereum, for example, basically everything is public: all transactions, all addresses, smart contract code, and in particular state variables. By adding fhE to the mix, we get what we call the fhEVM blockchain, an fhEVM blockchain, where we still have all transactions public, all addresses public, smart contract code public, but where you can choose state variables to be private. And this is the setting we're in. So this basically affords a lot of new opportunities, and this is what the talks earlier today and yesterday and so on has been about, what we get once we are in this situation. So I'm not going to motivate that again in this talk. Before we dive into the details of problems in relation to key management for this, let me just rehash broadly what fully homomorphic encryption is. Basically, it's the setting where you have a public key encryption scheme, where you have a public and a private key, where parties can encrypt whatever they want on the public key, and only the holder of the private key or the secret key can decrypt. However, what makes schemes fully homomorphic is that the ciphertext can be computed upon. So we can have parties from different places in the world, different users, whatever, encrypt different pieces of data, and then execute any kind of function on this encrypted data, which can then later be decrypted. And this is basically what we do in the fhEVM. However, what then comes up with this is that composition of ciphertext basically only makes sense if we have one public key. Like the reason is, if we take this fully homomorphic encryption and put it on the EVM, we want different users to use the same smart contracts. We want the possibility of smart tracks to communicate with each other. The only way we can allow this is if everything is under the same key, because you cannot compute on something that's encrypted on one public key and another one. So we get a single point of failure here, which is basically the secret key. Like we have one secret key, and we are in a decentralized setting, right? We work with blockchains. We don't want a centralized point of failure. We don't want centralized security. So this is why we end up needing the Zama TKMS. We need to be able to manage these secret keys in a very secure way. So what we are doing here very broadly with the Zama KMS is we're introducing a highly secure decentralized tool for managing these kind of keys. So this means that any L1 fhEVM, the coprocessor, which we're also introducing here this week, or any Web 2 service, whatever that uses fhE to achieve a goal, can rely on the Zama TKMS to do the key management of the secret key. What we achieve with this broadly is we get a way of managing the private key without any centralization. We can construct this in a way that's resilient to denial of service attacks, and where we get verifiability and auditability of whatever actions that gets carried out using the keys. So as mentioned, this unlocks a lot of situations, not just the fhEVM, not just key management on the fhEVM, but other cases where, like business-to-business use cases, Web 2 use cases, different kinds of governmental or statistics use cases, artificial intelligence, AML, defense, and healthcare. On the high level, the components, the ingredients we have in the Zama TKMS is that we take different tools which affords different kinds of securities and features we want. We use a proof of authority blockchain in order to get audit logs and verifiability, along with the traceable management. We use threshold secure multi-party computation in order to get a decentralized way of actually managing the secret key. We use secure enclaves on top of this in order to enhance security and protect even against malicious host and party. In a similar manner, we combine a legal framework to have legal contracts of service for the parties which act in the MPC protocol and which act on the POA blockchain. So that's broadly it. Done. Any questions? No. So this was the high level of why we need it, what we get, and the tools we use. So with that out of the way, now that you have sort of an idea of what we're talking about, I'm going to dive a bit more into to the detail. So historically, there's a bunch of different ways you can do key management, basically in any kind of way. You can use the legal framework of basically having contracts where you pinky swear that you won't misuse the key, do anything bad, and perhaps you can pay enough money that you trust the people to actually keep things safe. Certain businesses rely purely on that. It's simple, it's cheap, it's fast. It gets a notion of security, in particular the current legal system and where you employ things. You would be able to use it with any kind of code. You could do it open source, custom algorithms, whatever, because you basically just have a legal contract to ensure things are okay. Sometimes we don't always purely trust legal contracts, in particular when we cannot always see if something goes wrong. We cannot see if I sell my key to another party or I decrypt just one ciphertext. So there are other means of getting key security. Another main one that has been particularly common in the financial sector is the use of hardware security modules. It's generally simple to use. It's basically a solution sold in a little box that you plug into your server rack, and that's basically it. They're very expensive though. They're not cheap. To get reliability and a good throughput, you need quite a few of them because they are very, very slow. The security assumption you get with this is that you trust the manufacturer to have done their job properly. And I guess both as a trusted service, but also that even if you try, you cannot break into these things. It might be the case, it might not be the case. There's a bunch of techniques employed to try to achieve this, but it's a very hard problem that you cannot be completely sure of. Recently, there's been a lot of kind of HSM-based approaches, but not really, which is much cheaper, much more prevalent, and that's enclaves, like we know from our phones, laptops, and so on. They're simple, they're cheap, they're super fast, usually running in native speed, almost native speed on whatever processing unit you have. Like HSMs, they rely on an honest manufacturer, but unlike HSMs, it's easy to employ any kind of code. You basically just need to plug into whatever SDK that is being used for these secure enclaves, and that's it. Similar to the HSMs, they are gonna protect your key. Although since they're not as secure as an HSM, usually you have the same chip where you run normal processes and you run these processes. There's been a bunch of attack on these. And generally, security is more for like preventing malicious software of extracting information from your machine rather than me taking the machine I have, putting it electrodes and the chip and try to extract key information that way. So they provide more like a hardening rather than a full solution. Then finally we have MPC, Secure Multi-Party Computation, which is a very complex solution. There's a lot of code, there's a lot of mathematical theory and stuff you need to get this to work. But once you get it implemented, it's relatively relatively cheap since it's just software and a slight distribution. You may need some extra servers, but that shouldn't be too expensive, not if you compare with HSMs. The security assumption here is really strong because it can rely on mathematical provable security guarantees. Similarly, you can run whatever algorithms you want. You can keep it open source. And most importantly of all, this actually provides a decentralized way of doing things. And this is exactly what MPC does. It distributes the computation over multiple parties. This also gives an inherent resilience, which we don't get with the other tools. In the other tools, if the machine fails and it doesn't work. In MPC, you can have a certain amount of the parties participating in the protocol go offline, being actively malicious, and you will still be able to actually have the protocol execute. However, unlike HSMs and enclaves, the share is right there, at least in the basic implementation. So you could take it, you could misuse it, you could sell it. So these are like the typical approaches. So what we are trying to do with the Zama TKMS is, of course, to get the best of all the worlds, or at least best of all the worlds when it comes to focusing on security. So we are taking, we're taking the MPC, we're taking the enclaves, we are taking the legal framework in order to get a solution where we feel that we get the best of all the different security options we could get. And that's, yeah. That's overall the motivation we're having for this. So more specifically, we end up with in our work, we end up with a custom MPC protocol, which is provenly secure, robust by design. It can execute even if servers go online. It's based on peer-reviewed, top-tier academic research with some custom generalizations done by very elite cryptographer who's sitting in the back. And we furthermore add some optimizations and tricks to interface directly with Zama's FHE library, TFHE. We use, for now, Nitro enclaves on top of this to keep the key shares and execute the MPC protocol in this. So we're basically isolating the protocol execution to independent, secure enclaves. When I dive a bit more into the design later, you will see that the servers who are executing this are not accessible by the general internet and so on. So we get like both an architectural security in separation, and we get the security of enclaves as well as a prevention of running malicious code and stealing key shares. As part of this, we also did quite a bit of community contributions. Basically, at Zama, we do open source software, and we try to also contribute to the general community and do some good. And for this, we have published several academic papers, which we end up using in the whole S-TKMS system. We are also in the process of working on a proposal for standardization for NIST for threshold protocols. And once we enter a bit further down the line, we are open sourcing all the code as well for everyone to see and to use and possibly contribute to. So if you're not familiar with MPC, just as a high level, how the structure would generally look, it's something like this. You have a set of different servers, and they're basically communicating with each other. And this is how we start our whole system with the key generation. So remember I mentioned we have one public key. We never want the secret key to exist in plain anywhere. So our MPC solution is not just for decryption, but also for key generation. So we are executing this whole protocol to sample a public key with key shares on each of the different machines. All of this, again, is being carried out in the Nitro enclave. After this, we're managing the storage of this using, at least for now, S3, but we can eventually add whatever storage framework you would like IPFS, Filecoin, classical file server, whatever you kind of want. We basically use this as a public and private storage. Public storage for the public keys in order to ensure availability, so it's not just reliant on one host, one server, even when we use something that's not a decentralized storage protocol. We can also keep the encrypted key shares on this with a key that's stored in the Nitro enclave associated with each party. This allows for easy swapping of machine. It allows for horizontal scaling once you're actually trying to deploy this. The way this whole thing then gets linked to the fhEVM is through each MPC server signing the result, in this case signing the public key, posting it on the blockchain. The reason we don't post the entire key is that in fhE they're pretty big and space is pretty valuable on blockchains. And we want to be able to support anyone who wants to generate keys. If you want to generate a key for a specific application, you can do that. So we don't want to just log everything down to a single key. So this is why we have this design. Decryption kind of work in a similar manner, like key shares are fetched by each of the MPC servers using the Nitro enclave from the storage. They execute in the enclave the MPC decryption protocol and do a multi-signature on the result to get consensus, and this can then get submitted back to the fhEVM blockchain. For re-encryption, which is something I haven't mentioned before, re-encryption basically means those situations where you are a user and you want to decrypt a ciphertext, but you don't want to show the whole world, right? Everything that like a decryption of something that goes on the blockchain and only goes on the blockchain and everyone can see it. But if you are, for example, implementing a smart contract for confidential tokens, you want to know what amount you have. You don't want to share this with the whole world, right? So we need support for a way of decrypting to a specific user as well. And this is what we call the re-encryption. Re-encryption because we basically do a decryption and re-encrypt it on the public key only known by the user. When I say decrypt, it doesn't mean the servers ever learn the plain text. This will never happen in this case. They do what we call a partial decryption, execute almost all of the MPC protocol, and since basically let the user do the last step based on what they've done. Okay, so for those of you who are a bit more MPC focused, like some slight details on the actual MPC we're doing is that we have a protocol which we need to do some pretty tricky things. This is why it's not completely trivial to just take any academic paper. In particular, we need sampling of random bits over a large domain, which in this case is not just a prime field, but an extension field of 2. Which is also, for mathematical reasons, pretty tricky to get to work in MPC. So there's a bit of trickery that needs to be involved here. We also try to design things so general that it works with any different amount of parties. And the focus has been on cryptographic resilience in the sense that even if one server or some servers are sending bad information or simply dropping off, that we can still complete the decryption or key generation protocol. So we basically achieve what is called a robust MPC protocol or guaranteed output delivery. The protocol also has simulation-based proofs, which is basically the most desired style of proofs you would want in MPC. We furthermore achieve a feature, which I won't dive too much in detail into today, but we achieve a feature which allows the servers in between each other to refresh the key shares such that if one server gets compromised at one point, we can basically refresh everything without changing the public key, and then those key shares become useless. This is known as proactive security. We have two different kind of protocols. One where the amount of servers is low, and one where it's high. There's a cutting off point there, which is of course based on the hardware and so on. But we're trying to keep things as general as possible. So this is why we have actually done everything with two distinct kind of protocols. And there's an academic paper for that, which you can find on the link there on ePrint if you're interested. All right. So this was a bit more about about the design based on the MPC aspects and so on, how we achieve the features we want and why we actually need it. What I sort of scooched over is how we actually want to integrate this more on an engineering level. So this is what I'm going to try to talk a little bit about here. So first of all, how do the MPC servers get paid? How do we update which servers are actually doing things? We need to be able to run this indefinitely. So in a similar manner as a blockchain, we need, people need to get paid for their services. We need to be able to update the people as well. And how does this actually link to an EVM or an fhEVM? And do we need one? Do we need servers for each one of these? Each EVM we want to launch at? Yeah, so a lot of good questions. Diving a bit into it, it basically turns out that a blockchain is kind of almost the answer to everything. Payment, you can handle, if you embed a blockchain into this, you can handle this through tokens. Management, you can handle through a dApp or a DAO on it. The auditability of the actions of the server basically becomes, is a public ledger that is exactly that, like an incorruptible at only ledger of logs. The linking we can handle in a similar manner simply via smart contracts. And because of this, we can have one management blockchain, and then that can handle an indefinite amount of EVMs, fhEVMs, co-processors, Web 2 applications, business-to-business applications, or whatever. So that's basically, that's how we handle this. So basically the whole situation is, depending, you have a bunch of different L1s that want to use the TKMS, not necessarily L1s, it could also be a Web 2, an L2, or whatever. And the way we do this is we launch this threshold TKMS blockchain, where each of these services deploy an application smart contract, which is used to manage everything. So this is also how they would initiate key generation for their specific application. So this happens through this contract, which also allows to facilitate payment to the MPC servers in a similar manner. So now I added another blockchain to a blockchain. So if we all know anything about blockchains, it is, well, storage is a bit critical, latency is usually a bit low, throughput is also a problem, so aren't we just shooting ourselves in the foot? I would argue we are not, but in particular, because we are in a setting here where we link this to MPC servers, we have a lot of, what should we say, leeway we can take. However, we also have some constraints, right? Because this needs to integrate with an EVM. We really need this to work with a low latency. We need to work with a high throughput since we want to support multiple chains. And also, we need fast finality. However, we don't necessarily need everything to be Turing complete. We can actually do this in a permissioned manner, since we already need to trust the MPC servers. So we're already in a setting where we don't allow basically everyone in the world to join a huge protocol, but when the set of a small amount of somewhat, not completely trusted, of course, but somewhat trusted servers. So because of this, we have a lot of leeway in how we realize this. For our specific case, for now, but this is, of course, something that can be changed. We're using, basically using Comet BFT, and we have set it up with latency and finalization of about 1 second. So this means we can do things pretty quickly. For now, we are using basically validators, as many validators as we have threshold servers, but this can be varied in the future, can be launched on another blockchain in the future as well, if that's what we want. So it basically means that now we have reduced the issue to cross-chain communication, basically. We need to communicate from an EVM blockchain to the KMS blockchain. For this, we need an extra component, which we here call the gateway. The gateway will be a non-centralized, and it is basically, it's untrusted, right? Everything that is happening is validated through signatures and trust based on what's happening on the MPC servers. So this gateway, or on the fhEVM, so this gateway is just relaying information. So anyone would be able to launch one of these, and the trust comes from the cryptography applied on either side. So yeah, you can have more. Diving slightly into some technical detail on how the actual validation and communication happens between the fhEVM and the threshold KMS blockchain. We're basically using an access control list on the fhEVM that contains a Merkle tree of the ciphertext, of the permissions of the ciphertext to be decrypted. Which is kept, whose root is kept in the header of the block. These are basically communicated over to the threshold KMS blockchain initially when everything is set up, and that's how the threshold KMS blockchain validates requests are actually legitimate and don't ask them to get carried out by the MPC servers maliciously, basically. When it goes to the other way, we have a slightly curious feature in the sense that the fhEVM as such only needs to be fully aware of the validators and on the TKMS blockchain when they set up, when they launch the whole thing and get the key generation. For decryptions, everything will be based on trust of the signatures from the MPC servers, which can be validated on the fhEVM chain. And this is also through smart contracts on this relayed through the threshold KMS server is how the fhEVM keeps being aware of what is trusted, which servers are trusted, which are updated, and so on the threshold KMS blockchain. So this means that we can now put up the whole end-to-end flow of the TKMS. In this example with an fhEVM layer 1, goes through a gateway. That can be multiple instances since they don't need to be trusted. They cannot destroy, well, they cannot make changes without it being detected. Goes over to an application smart contract on the threshold KMS blockchain, which emits an event that gets picked up by the MPC framework, which executes the MPC protocol in a Nitro enclave and is using, at least for now, S3 for storage. All right, so we're still in the early stage of this, so I just wanted to give some idea of the efficiency we can expect from this. So I brought some very, very preliminary numbers for the time it takes for the different types. So let me explain a bit more what it is here. Besides launching the decryption in the threshold KMS as a full threshold MPC network, we're also working with a proof of concept or also deployable centralized version. So these are the T1 numbers here. So this means that it's not the threshold protocol, it's just one server that's executing things in Nitro. The T4 here is for the setting with 4 servers, corruption of 1 handling. That is executing only the decryption. So on the core cryptographic side, these are the numbers we have here in the engine, which we call the engine. So we see, of course, for centralized, things are very fast for decryption, unless we go down to like the really big pieces. For the T4, we still get quite high efficiency. For like reasonable sizes. Of course, things get a bit slower when we get to the big end. The numbers over here is the whole end-to-end flow. This one, the first one here is the end-to-end flow for the threshold KMS. So once it's on the threshold KMS blockchain, it goes through the MPC network, goes back to the blockchain. We get these timings. The end-to-end to fhEVM, that's the same as this one, plus the extra time of getting things back to the fhEVM. These are for T1, but as you can see, since the latency getting higher by using the threshold is quite minimal, the changes will be quite minimal if you execute this even with the threshold background. But again, these are some very preliminary numbers. It's not like full average benchmarks. It's just it's based on tracing from versions from last week, basically. But I just wanted to make sure people have an idea of which kind of latency we can expect once we move on with this. Some final points about security. I think I iterated this, but I think these are the main points, especially when you do a presentation about key management, is that we get secrecy, correctness, and reliability in a distributed manner without a single point of failure or trust. Secrecy and correctness can only be broken if more than a threshold of the MPC servers or the validators on the TKMS blockchain is corrupt. Reliability, the same. Although reliability, of course, also fails if all gateways refuse to work out. Of course, these are based on the clear assumptions, that there's no mistake in the cryptography, the code, or the EVM, or that, of course, that the threshold assumption is being kept. So these are just like the constraints, which are the reasonable best constraints we can kind of hope for in this situation. And all right, so some further considerations in relation to security. One thing I didn't touch upon in this presentation, which you also need to be aware of if you want to get security, is malformed ciphertexts. This is inherently not something the TKMS is responsible for. This is something that should be handled on the fhEVM, which we do handle on the fhEVM using a custom zero knowledge proof of knowledge of the encrypted, of the input of a ciphertext. This, such a zero knowledge proof ensures that whoever posts a ciphertext actually knows what is in it. Why is this needed? Well, so I can't just pick any ciphertext on the blockchain and post as my own, basically. It's also needed to prevent some subtle selective failure attacks where the decryption will fail depending on a specific bit of the private key. So these kind of things are both needed in relation to privacy, but also for avoiding extraction of the secret key. But this is inherently something that is on the that is handled on the EVM side and not on the TKMS side. But it's something that's very important to be aware of when you're looking at systems like this. As I briefly touched upon earlier, we are also supporting a refresh mechanism, meaning that even if one of these threshold servers do get corrupted, get the key share stolen, we can execute a pretty efficient protocol, efficient as in like seconds, to refresh the key shares amongst the different servers in order to ensure that the old pieces basically become useless without rolling a new public key. This is a very useful and very powerful feature, which is, I believe, is kind of essential if you want to run things in the long run without having to re-encrypt everything. All right. So, as mentioned, we're still in an early stage of this, but we're very excited about it, and we wanted to share it with everyone as soon as possible. So here's a slight status of where we are now and what is coming soon. So the whole presentation I did today is the features and the setting we want once we actually launch. We are very, very soon going to share Docker images for a pre-release, which of course doesn't have everything. And this is what is reflected here. What we basically been going through in relation to the cryptography is all the MPC is done, the zero knowledge stuff is done, the FHE stuff is done, all the PKI stuff is done, TLS is done. We don't have a full internal or external security audit yet. This is something we work on. So far, we have been trying to work hard on getting the core cryptography done and the functionality, as we believe these are the most important things to get started so that everyone can start to play with it and we have an idea of the efficiency. When it comes to the infrastructure, the launching of the TKMS blockchain is done. The smart contracts needed is done. We're deploying things on AWS also. The Nitro version is done for the centralized stuff. And we are working on getting it also fully deployed. S3 storage and horizontal scaling is something we will be working on soon. End-to-end communication is basically done. On advanced features, which will come later, is actually having a full flow, integrating in smart contracts with these refreshing protocols. This is something we're working on. As mentioned, we want everything to be open source. It will also come as this, but it's not there right now. What we're initially launching is a version without using all the threshold stuff, because this was simpler from a deployment point to get everything to get going, to find out the problems and so on. And very, very soon we have the fourth party version ready as well, and eventually it will be scaling to arbitrary amount of parties. Yeah, so with this, basically, if you want to use it, we will offer it in different ways, either as a service we host here at Zama, or you can do it self-managed, where you basically get the images. You're responsible for the deployment, so you can use whatever system server that you want to run things on. And of course, since this is going to be open source, you can also use, have a look and play around with it yourself. So yeah, with all of this, it's the whole flow of actually using this whole thing is like configure it based on the smart contracts on the EVM, or if you use our hosted version, generate the keys and basically deploy and work with it. So yeah. Very, very soon, we get some initial documentation out. We get some Docker images out. A little bit further down the line, we get the white paper on this out. It's still in a draft version, and we're working hard on getting everything of this done. And that's it. Thank you. Questions? I see Job already has one. Yeah.
Do you use the Nitro attestation feature to prove what code is running in the Nitro enclave?
Can you repeat the last part?
So do you use the Nitro attestation feature to prove that the correct image is running in the Nitro enclave?
It is on the schedule. Yeah. We are working on also deploying with this. We're also using it. Both in relation to the correct image and also just the secure execution. Both. Yeah.
Does it mean that the throughput of the fhEVM will be bottlenecked by the throughput of the TKMS? Because I'm thinking like if there's a burst of decryption requests, they have to wait for the TKMS to like fulfill that, right?
That's an excellent question. Basically, the way we are deploying things in the fhEVM when we're releasing, the previous versions had a synchronous way of doing this. We are moving towards having everything be done asynchronously. So once you send us to decrypt in your smart contract on the fhEVM, you will have to wait for the reply to come back from the whole network. So it doesn't happen within the same block.
Got it.
I'm wondering, this seems like an iteration on top of the Torus network, Web3 auth. I'm wondering how do you guys, not that you differentiate, but what are the additional features? How have you guys kind of incrementally innovated on top of those previously defined infrastructures?
So I believe like the main feature of what we're offering here is the fact that we are deploying with robust MPC. So meaning that we're able to handle malicious corruptions without interruption of service. I think that's like one of the main things we are doing with this compared to existing solutions.
I'm quite surprised by the refreshing process.
Yeah?
Can you elaborate a bit?
On a technical level?
What surprised me is that you don't need to recreate a new key.
Right, like the key is split up in secret shares, basically Shamir secret shares. What you can basically do is you can redo resharing each of these shares, like you re-randomize everything basically.
Okay, but you need at some point to gather all the shares at some central point.
No. You can do it non-interactively. Of course, there's more details, but simply I can imagine like I have a share. I basically just share it with the correct degree with everyone else. Everyone else does the same. We execute a procedure to validate that things have done correctly. Now we have refreshed.
Okay.
I just wanted to add something also about how we're differentiating. It's also new that you can do that for TFHE key generation and decryption in a threshold way. So, it's not signing stuff, right? We're talking about fhE key generation, decryption, and also the fact that we're actually doing that as a blockchain. So there will be like a live blockchain network offering threshold key generation and decryption based on that, which comes with this whole set of other questions, but that's the idea.
Thanks, Ryan. Yeah, that's a very good point. Like basically what we're doing is we're taking advanced cryptography and applying advanced cryptography to advanced cryptography. So we have a lot more challenges than just doing ECDSA or even El-Gamal encryption, things like that. Like we need to, our MPC stuff, we need a fully fledged suite. We could take whatever we have in MPC, and instead of doing fhE, we could run everything with MPC, right? Like we have needed the whole general thing because of the complexity of doing threshold generation and decryption of fhE keys.
To give you a bit of a sense, out of like the 75 people working at Zama, there is close to 20 people working on this thing end to end. So it's actually way more people than people would think we have working on that thing. So Zama is an fhE company with 20 people building an MPC protocol at this point. So
it's interesting to be able to be to be able to have a non-custodial key that's assembled on your own device without having to trust any one provider. And as far as I could tell, there's Magic Link and Web3 Auth that do it. Maybe there are others that are doing it. And I'm wondering, with your implementation, do you anticipate there be dozens and dozens of similar companies that are kind of riding on top of your infrastructure to create similar offerings?
That's a very good question. I'm not sure. I guess we'll see how things go. I mean, of course, if they want to use our technology, they're welcome to contact us and make a licensing deal. I mean, that would be great. Like the more traction we can get in the environment, the better. I mean, this is also just like the initial of what we're getting. Like we're using this to facilitate fhE as an initial goal. But the space moves fast. There's a lot of innovation to happen here, and that's great.
Do you anticipate those types of clients to utilize or those types of companies to utilize your infrastructure?
I honestly don't know. I don't know, Rand. Do you have any idea about that?
Yeah. So what I can tell you is I thought it was going to be way easier than what it actually is to build this and deploy that. I think a lot of people think about deploying an MPC protocol as just the MPC part. They don't realize every single other bit, right? Even just finding reputable people to run those nodes, right? Just convincing them to do that for an unproven thing. Like, there's so many layers that goes beyond just the core cryptography to make this something that people actually trust in terms of using it. I think that we're going into very uncharted waters here, and so if this, once this works, because it has to work for everybody doing fhE, obviously. I think there's going to be very little incentive for someone to try to rebuild the same infrastructure versus just leverage it and build stuff on top. I think there's something in blockchain in general that we love building infrastructure, but you also have to think about building products on top of these things. And so we're hoping that people will focus on building products as opposed to just redoing something that works. Yeah.
Okay, so so the difference between like the MPC here and the MPC you would have for threshold wallets and stuff like that is very different. So the key that you have for a threshold wallet is protecting you as an individual. So it's your assets, whereas this is protecting keys for a whole blockchain, and the whole blockchain has to have very, very high availability. So this creates this incentive, well, not the incentive, the requirement is robust. And that robustness means that these MPC protocols are orders of magnitude more complex and more deep than anything that's been deployed to do MPC for threshold ECDSA signatures. This is a whole level of complexity. And then you have all the systems complexity that Ram was talking about.
Is it still intended for end users?
The end users use it, but the key stuff, all the MPC stuff, is not for end user secrets. It's for, it's the system's secrets.
the customer, the KMS, is basically the DApp with the blockchain. And the user interface is for that. We imagine that a person paying for decryption is going to be the DApp company, not the end user. And then, if you want to delegate that to the user, you can do whatever you want to your product.
Oh, for the record. Yeah, sorry. Yeah, maybe my understanding is a bit off here. But if I understand correctly, you said that only certain actors that you choose can join the MPC, this TKMS blockchain. Is that a problem from a security standpoint? Because, I mean, you are choosing, you can choose a bunch of your friends. There's a trusted, there's a security assumption here, no?
So the problem, first of all, if we could do this completely decentralized, permissionless, with some kind of proof of stake mechanism, that would be ideal. We have actually some research work ongoing on how to do proof of stake within MPC threshold protocols. There is no construct yet that allows that for one reason, is if you put this up in the air and there is no way for you to know whether people are colluding off-chain, off-protocol, right? There is no way to know if people are colluding off-protocol. And so you cannot just put this in the wild and hope that people will behave. So until we figure out the solution to that, which is the goal is to enable anybody to join, the best we can do is say, okay, first of all, it has to run in an enclave. So you need to simultaneously break enough parties and enclaves. And here the enclave is AWS Nitro, so you have to get Amazon to basically collude with enough parties, which I would agree, I think we can agree is not going to happen. Amazon is not going to collude with random MPC nodes. Amazon has 100 billion of revenue at stake, right? So I don't think that this is something meaningful for them. And the second thing is having doxed reputable people, right? If they get caught cheating, they have enormous reputational or money risk here by doing that. I'll give you an example. Some of the nodes that are going to be running that are going to be blockchains which themselves are using it. If they get caught cheating, I think nobody will ever trust using the protocol again and their token will crater. So you have, I guess, indirect economic security by knowing exactly who has been participating in the protocol. So again, it's honestly the best that can be done today until we figure out a way to do secure, permissionless POS type MPC protocols.
What do you think would be the ideal solution in
Decentralized, permissionless, proof of stake type MPC, but I don't even think it's possible.
Do you think we would need some special physical devices?
I think you'll need an enclave or an HSM. You'll need some kind of special hardware no matter what. I don't see how you could ever get around that. If people can just get the file from the hard drive and call each other on the phone, how do you prevent that,
Well, hardware that produces some special verification or something like that?
That's effectively what the enclave tries to do. But to be fair, I think, so when you look at the enclaves, you have HSMs, which are super, super hardened, but extremely slow and very difficult to configure. So it's not very amenable to upgrading very quickly. You've got SGX type enclaves, which are broken effectively. And then you have, in this case, Nitro, which isn't actually run by the node, it's run by Amazon. So even if the node is malicious, they still can't get access to the content of the Nitro enclave without Amazon giving them access. And so that's why I'm saying that you have a different level of security by trusting AWS as an enclave as opposed to trusting some hardware that you can just plug in an oscilloscope and try to side channel. So these are super complex questions. I'm going to be very transparent. We are kind of solving those problems for the first time. I don't think it has been done before. And this is the best that our team could come up with the existing technologies.
Just to add on what Rand said, you can also add other cloud providers. It doesn't have to be Amazon as such, right? Eventually you can add whatever other provider, as long as we still have an option of using these secure enclaves. Besides that, we're also actively looking into incentives in order to enforce honest behavior. In fact, we have an academic paper in review process right now about detecting rogue shares in general. Like, it's a very hard and very important problem in this decentralized space when you're talking about key secrets. There's a lot of not just commercial research, but also a lot of academic research happening on this at the moment, and as mentioned, Zama, we're also actively contributing to all of this this research effort. So, I mean, we're working here with the initial. Things will only get better as we come along, as we get better approaches to enhance security, to integrate everything with incentives, and so on.